Well, good morning, everyone. This is Rick O'Connor from the OpenHW Group, and we are about to kick off a live stream for today's episode with some of the fun that we had in Embedded World in June. So we're going to live stream some presentations from the Embedded World conference back in June, and in particular, the launch of the CORE-V MCU DevKit. And today on the webinar with me is Richard Berry from Amazon, AWS. And we're going to have the live stream come on in a minute here. We're going to watch, obviously, with you together, the rest of the attendees. Richard and I watching with you. And then that'll take about half an hour or so. And we'll come back live for some Q&A with the attendees. So over the course of the live stream video, as you see things that trigger some questions, please enter the questions in the Q&A panel in the Zoom app here, and we'll take your questions live and have a discussion at the end of the episode. So thanks for joining us, and here comes the live stream.
If you want to come in and sit down, we're going to talk about the open hardware ecosystem, where we're building open source RISC-V cores for use in high volume production SoCs. So my name is Rick O'Connor. I'm with the OpenHW Group, and we have a guest speaker today. Richard Berry will be up in a couple of minutes from AWS, talking about how we're using the cores to connect to AWS Cloud. So a couple of slides on what the OpenHW Group is, what we're about. So it's a nonprofit ecosystem made up of developers from around the world, hardware engineers, software engineers collaborating on the implementation of open source, a family of open source RISC-V cores called the CORE-V family that are well-written system Verilog cores, fully verified using traditional commercial industrial grade verification methods. So you can take these cores and use them in high volume production SoCs. So it's a very large ecosystem. We've got 88 members and partners from around the world. Many large systems companies and silicon companies and smaller companies and chip guys, systems folks. A lot of participation at the corporate level. A lot of participation from academia and universities from around the world, and a very healthy list of partners as well. And the way that we're structured is through a series of technical working groups and marketing working groups, and then in particular, a bunch of task groups underneath those working groups, where all the engineers from collaborating companies work on defining projects that they want to implement, and then implementing those projects under SolderPad licenses, Apache licenses, or the Eclipse public license in terms of open source artifacts. And in particular, we have something in the neighborhood of 24 different projects now underway in the ecosystem. Again, all of this is open source. You don't need to be a member to use it. It's true open source. Just take it, download it, have at it. Obviously, if nobody contributes, then there's no ecosystem. So the membership is part of what glues these member companies together. And it's the members who decide what projects get worked on. So they agree on the features and functionality in the projects and then collaborate on the development of those projects. And one of our more active task groups is the CORES task group. And they're responsible for the CORE-V family of open source RISC-V cores. And the original cores started life at ETH Zurich. You might be familiar with the Pulp platform work at ETH Zurich under Professor Luca Benini. The RISC-V core and the Ariane core started life at ETH Zurich in that team, and were contributed to this open ecosystem a couple of years ago. And they've been steadily being improved and extended through verification and new feature additions. So as I said, the roadmap is pretty healthy. We have 11 different RISC-V cores or variants in development right now in various stages of development and production and verification work. And I'm going to focus on the CV32E40P. That's a fully verified core. It's like a Cortex M4 class embedded style core, and that's what's used in the CORE-V MCU. So with that, I'm going to jump into what we're actually talking about today, and that's the development kit around an open source MCU that we announced today at Embedded World. There's a bunch of articles that went out this morning. We have development kits sitting in our kiosk. There's one over at the Amazon booth. There's one in the DigiKey booth. There's one in the Embocosm booth, and then a whole bunch spread around the world. This is the group of companies that have collaborated on this project, so it's a very healthy group of companies. And what we're doing today is emulating like a global weather fleet station or a weather station fleet. So if you have your, whatever your IoT device is, say refrigerated cargo or something, and you're monitoring temperature or the conditions in the refrigerated cargo around the world, that kind of an application. The point of this demo isn't that, oh wow, we know how to measure temperature and stream it to the cloud. That's not that interesting. The fact that the whole thing is built on an open source stack from the RTL into the cloud, that's what's interesting. So we've got these weather station fleets spread around the world. Like I said, there's a couple here, a bunch here at Embedded World. And I'm going to start from the inside out and right down at the core and come all the way back up to the cloud and talk about each of the pieces along the way. So the core is the E40P core. This is a fully verified. We have the coverage-driven reports available on our GitHub repo, functional coverage, code coverage, assertion coverage, fully verified and ready for high-volume production SoCs. It's being used in at least half a dozen different commercial SoCs that have been released since this was done. And we took that core and integrated it into a very simple MCU with very, very generic peripherals. The point is, it's a real-life example platform. This is being built in 22FDX. Tape-out is any day now. We expect silicon back in the late this year. And what's interesting is there's an embedded FPGA array attached to the core. So you can use the FPGA array, attach your own accelerator for your own particular IoT application that you're trying to process and accelerate and explore that. And then we take there we go. We take the MCU. Right now we're emulating it on a Digilent FPGA board, and that's the demo kits that we're showing here today and that are connected into the cloud with these temperature sensors. So these hardware emulation platforms are running FreeRTOS on top of the MCU. Both Ashling and Embocosm have contributed heavily to the toolchain and IDE. So we've got a CORE-V SDK that includes an Eclipse-based IDE to program the MCU, running the GCC compiler work from Embocosm. And you can see that running over at the OpenHW kiosk if you want to come and look at that later. And that makes up each individual weather station. So the MCU and the temperature sensor over here running the FreeRTOS OS, connected into the cloud using Amazon's new ExpressLink interface, which runs on an expressive Wi-Fi radio connected to the MCU via UART. And with that, I'll hand it to Richard.
Thank you. I'm just going to talk very quickly about the cloud connectivity on the DevKit. Now, with cloud connectivity, hopefully number one priority is security, and that means that you're going to need TLS, secure storage to hold the keys for the TLS, secure boot, etc., etc. Now, FreeRTOS provides everything you need in order to effect that secure connection. And what I'm trying to represent here is the libraries that we provide. This is just a subset, because obviously it'd be too big. We try and make this as easy as possible for you by having each individual library completely self-contained. There's no dependencies on anything other than the C library, for most of them anyway. So that means you can use them any way you like, whether you've got a package manager, Git submodules, SymSys packs, or anything like that. But the point is here that you have got quite a lot of functionality. The TLS stack is quite a big thing, right? Then you've got TCP, MQTT, HTTP. And what you find is that your undifferentiating code, just the stuff that you need for cloud connectivity, becomes much larger than your actual application code. So what we've got on the evaluation board is this new product which we actually announced in December last year. It's gone GA today, by which we mean generally available. It's no longer in preview. And what that does is build all of that cloud connectivity software, the TCP, MQTT, over-the-air updates, everything you need. It's got the keys that you require to get a mutually authenticated cloud connection. You can buy it with those on there. It comes with a unique identity. It takes a lot of that away. So as much as we try and make our libraries as easy to use and as modular and take the software to you as much as we can, this is really a step change in ease of use. So you think of the individual libraries, you've got an infinite combination of hardware and software that they'll work with. If you're having a radio on your device already, Wi-Fi, cellular, then by using one of these AWS IoT ExpressLinks, all you need on your microcontroller is a UART. So if you can do retrofit even, and all you have to do then is send to the UART a string that says AT connect, and it will do all of the TLS negotiation for you in a secure way and generate that cloud connectivity for you. So we're demonstrating this on the AWS booth, and it's also on the DevKit.
Thanks, Richard. So the other thing to note here is, for a lot more detail, Richard's in the theater, in Hall 1, just at the end of the aisle here, at 4 o'clock, I think, right? Giving his FreeRTOS deeper dive talk. So thanks for stopping by, and thanks for your support from AWS, Richard. Okay, so just to take you back a second, so this is just one endpoint, right? We add a bunch more, and then we're streaming this up into all the AWS database tools that sit in AWS Cloud, and then running a little dashboard on Grafana just to demonstrate what the temperature is for all the different endpoints around the world. So there's one set up at the QuickLogic office in Austin. There's one set up at our OpenHW office in Vancouver. We're spread all over the place. And you can come around and see them all live there now. But like I said, that's not a huge technical feat. What's more interesting, in our opinion, is the fact that this is all built on open source artifacts, right from the RTL of the core itself to the MCU, the FreeRTOS, the IDE, the GCC work, all the way up into the cloud. So we think this is a pretty cool application of open source implementations. And if you have questions for us, please make sure you stop by at the OpenHW booth. And this will all show up on a physical board. We're building this, like I said earlier, in 22 FDX with Global Foundries. They're a member, and we love Global Foundries. They're a member of the OpenHW ecosystem. You can go to our DevKits page to see some of the other DevKits that we're developing in the ecosystem. And GroupGets is managing the early access campaign for this board. And you can register on their site to be notified as soon as the board actually launches and is ready for order. And you can get these details over at the kiosk if you want to come and see us, or you can ask questions now as well, because that is my last slide. And did you get your picture, or did I go too fast? I could back up. There you go. Everybody wants a picture of this board. You know what, I can send you the picture. There we go. So I think we have a good amount of time for questions. Well, come and see us at the kiosk over the next couple of days. Thanks very much for your time.
Good afternoon. I'm on site here at Embedded World 2022, and joining me today is Rick O'Connor, President and CEO at OpenHW Group. So thank you very much for joining me today.
Thanks for having me, Paige.
Now we're going to be talking about OpenHW Group's RISC-V-based CORE-V MCU Development Kit for the IoT, built with open source hardware. Now the latest development in RISC-V that you're showcasing here at the show is the RISC-V-based CORE-V MCU Development Kit.
Yep.
Now before we go into more detail on this, could you just define what is meant by CORE-V?
Yeah, okay, sure. So the CORE-V brand or name is the name that the ecosystem is using for a roadmap of open source cores that implement the RISC-V ISA. So we have, there's roughly 22, 23 projects currently underway within the open hardware community. And of those projects, there's 11, I think, 11 different cores in the CORE-V family, from very small, deeply embedded size cores to higher end application cores and vector processors and so on. So they all fit underneath the CORE-V family.
Right, okay.
And that 5, Roman numeral V kind of thing is, or V, Roman numeral 5, is a play on RISC-V, the V in RISC-V, which stands for the 5th generation of RISC architecture research at Berkeley. So we just borrowed the 5 from that and called it CORE-V.
Excellent, very clever. Now, using any previous RISC-V technologies for a point of comparison, could you introduce this development kit for us and tell us what makes it different to preceding RISC-V technologies? Right,
so this CORE-V MCU development kit includes a 32-bit embedded class 4-stage deep pipeline core. It's kind of equivalent in performance and size to like a Cortex M4 from ARM, just in terms of size to position it. But it's completely open source. So you could download the core today and throw it into your favorite design and away you go, right? No licenses, no lawyers, no fees, no nothing, away you go. It's licensed under the SolderPad license, which is a variant of Apache, and pretty much everyone's familiar with the Apache license. And that's really the fundamental difference. But it's open source with an industrial, commercial grade quality, if you will. The verification task group in our ecosystem has worked very, very hard at producing a test bench called CORE-V Verif, which is used to verify all of the cores in the CORE-V family. And the test bench is designed around system Verilog UVM techniques that commercial companies would use to verify their own IP for high volume use. So, on the one hand, yes, this is an open source project, but it's a commercially viable, ready for prime time production piece of IP.
Yeah, sounds great, fantastic. So the technology enables software development for embedded IoT and AI-driven applications. Would you like to walk us through some of the examples of what these applications are and sort of any significant benefits that you feel they bring to the end user?
Sure. So the first thing that we did was, so this is a Digilent Nexus 7 FPGA board that is a hardware emulation platform for the CORE-V MCU itself. So that core I was talking about, integrated into an MCU design, emulated in the Xilinx FPGA on here. And of course you can get these handy Nexus boards from your favorite Digilent distribution office as well. And then this is all enabled with an IDE built around the Eclipse embedded IDE, includes GCC, compiler, and FreeRTOS operating system. But the CORE-V MCU also includes an embedded FPGA array where you can embed your own accelerator, AI accelerator, machine learning accelerator right next to the core to enable all kinds of smart, power sensitive but performant requirement IoT edge applications, pattern recognition, facial recognition, video detection, all kinds of stuff. So it's a pretty powerful little platform.
The possibilities are endless.
Oh, well, there you go.
Now, the major project that you're focused on here at the show is to use the DevKit to emulate an array of interconnected weather station sensors, not just here at the conference, obviously, but even at various locations around the world. So could you give us an overview of how the DevKit has achieved this and how you expect such an exciting use of the technology sort of will translate to similar applications in the real world?
Right, so we're emulating a weather station fleet or some kind of fleet enabled with IoT sensors. So in this case, a temperature sensor. It's not that in and of itself is not the technical marvel, right? That's no big cheese, so to speak. But what we've done is integrated a Wi-Fi radio from Espressif that implements Amazon's ExpressLink protocol. So these development kits are connected into Amazon Cloud, and you can see that this board's live and running. There's boards at the Amazon booth. There's a board in the OpenHW kiosk in the RISC-V booth. There's a board over at the Embacosm booth all here at Embedded World. And then there's another 8 or 9 boards spread around the world at different physical events that are running in parallel,
Well, okay.
as well as in various offices of the different collaborators. And part of what we wanted to demonstrate was first, the scope of the global collaboration that's going on. We got these things spread all over the place. They're collecting temperature in each of their various locations, streaming it up to Amazon Cloud, being authenticated, and then we're displaying that in a Grafana dashboard that has basically all the IoT sensors and their data just streamed up, so you can see that collection of data.
Yeah.
And like I said earlier, it's not, we haven't solved world hunger here with, measuring temperature and streaming it to the cloud. But this is more, what's unique about this platform is this is open source from the RTL at the core right on through, right? Mm-hmm. We're running, it's an open source core on an open source MCU, running open source compiler tools on an open source operating system connected into Amazon Cloud, and developed by about 20 different companies, all collaborating in an open source public domain engineering environment.
Yeah.
And all of it to commercial quality standards, so you can adopt this IP and use it in your own high volume production SoCs.
Yeah, that's fantastic, and a great application example as well. So as you say, the project highlights the open source collaborative development. Could you run through sort of some of the exciting collaborations, as well as sort of any other features you'd like to share that have made this project a success?
Sure. So the cores themselves were born out of research at ETH Zurich University in Switzerland.
Yeah.
It's one of the more prominent engineering schools in the world. And this core at ETH was called the RISC-V core.
Yeah.
And under the Open Hardware banner is part of the CORE-V family. So that was a nice, well-written open source core, but needed to be verified. So we had a lot of work on the verification task group. Probably peaked out at about 20 or so different contributing companies on that work, working on the CORE-V Verif test bench that I mentioned earlier, with great contributions from Silicon Labs and Imperis and Embacosm and others. And then that core was taken and integrated in the MCU. CMC Microsystems and QuickLogic led that work in our hardware task group to build the MCU. And then, of course, you need all the software to run on that. So good work with our software task group, led by Jeremy Bennett at Embacosm and Hugh O'Keefe at Ashling, to develop the GCC tools, the integrated development environment based on Eclipse IDE, to develop the CORE-V SDK. And then there was the porting of the FreeRTOS, the operating system from Amazon on top of that. And then connectivity, the development of this board that sits on top of the Nexus card here. That was developed by Amazon as well. And integrating the expressive Wi-Fi radio to connect it all into the cloud. So this is really the culmination of a number of different individual projects within the open hardware ecosystem, all being brought together into this development kit that we're announcing here at Embedded World.
Excellent. Well, thank you very much for bringing it along to show us, and I'm very excited to see where you go in the future.
So am I. Thank you, Paige.
Brilliant. Thank you very much for your time, and enjoy the rest of the show.
Thank you.
Thank you.
All right, so welcome back. That's the end of the live stream portion, and we can take questions now from the attendees. So if you haven't already, please, enter your questions in the chat box, or sorry, in the Q&A panel on the Zoom app, and we'll take your questions. So I'm going to kick us off with a couple of questions for Richard. You've been on OpenHW TV episodes before, but maybe share with the attendees what the motivation is for the FreeRTOS team and AWS to participate in this kind of an ecosystem and use the open source cores from the CORE-V family for some of your work.
Yeah, well, I think our our motivation is to make sure that users have the best experience possible using the products. I think well, I wouldn't say everything. A lot of, well, I would say most of our roadmap is really driven by end users, and as you say in the Open Hardware Group, the committees kind of decide what is going to be worked on. There was a decision to use FreeRTOS, which we're very happy about. We want to help and ensure that as RISC-V grows, that the various different versions of FreeRTOS which are running on RISC-V don't become fragmented, and we can consolidate everything into like a single upstreamed version, which so we're working with the Open Hardware Group to actually, as we speak, upstream the support for your devices. And then hopefully we can ensure that we can provide people the robustness and the level of support that we provide, or we pride ourselves on for your devices as well.
Our devices, as an active member, they're yours too.
Yes, everyone's devices.
Everyone's devices, exactly. The community at large owns all of the artifacts. And talk about ExpressLink for a bit. I mean, to be honest, most of the folks that I come across are not yet familiar with what this is and why it's important to them, or why it should be important to them.
Yeah, so IoT is obviously still a very much growing area, and connecting particularly small MCUs requires a lot of different of what we call undifferentiating functionality, right? Just things that you need to be able to connect to the cloud. And I think I mentioned a little bit in the videos there, we try and make sure that we provide that software in the most portable way possible, because there's different compilers, different hardware architectures, of course, RISC-V being one. And you can be an expert embedded developer, top of your game if you're doing something like motor control, for example. But when you want to then get the value that the cloud offers for things like predictive maintenance, for example, or to be able to patch your devices over the air, then you're suddenly asked to add in all this undifferentiating functionality, which isn't necessarily your core skill. So that there can be skills gaps, there can be time to market issues, there can be there's just you have to, as simple as we try and make it, you still have to integrate the C libraries and then the API. So what we've done is offload all of that onto the radio chip itself, and then you can think of it as a modem for connecting to the cloud. If you're familiar with AT command sets, so instead of having to integrate all those C libraries, if you're going to have a radio on your device anyway, think Wi-Fi or cellular or something like that, you're going to have that on your design anyway, so there's no additional BOM cost. Running all of that connectivity software on there means that all you need to do is have a UART driver, and there's like one-time setup of saying what's the endpoint you want to connect to, which is just a human readable string that you send across as an AT command. After that, you just say AT connect, and all of the connectivity, the TLS connection, secure storage for the secrets required for authentication. That's the level of abstraction is such that all that's done for you, don't even know it's happening. It is really raising the level of abstraction. You don't know what the radio is. You don't know whether it's TCP or MQTT or anything. So it's very. I'm very excited about it because it just makes time to market and ease of use so much better.
Yeah, I'll comment on that in a second here. Just want to remind you for the attendees, please, fill our Q&A window here with some questions. I'll take any question you ask about the open hardware ecosystem or RISC-V in general, and feel free to put Richard on the spot because he enjoys that. So just put some questions in the Q&A window, and I'll just expand a little bit on the ease of use comment that you made. And there's no radio in the CORE-V MCU, as sort of we talked about in the dev kit during the videos. There's no radio on the MCU SoC itself. So we needed to, if we wanted cloud connectivity or Wi-Fi connectivity of any kind, we needed to put a radio down on our development kit board and then manage the stack somewhere, do something with it, right? So, ExpressLink was perfect actually for this development kit deployment, because it's like you said, literally UART driver and FreeRTOS that sends AT commands off to this just magic thing over here in the corner of the board. Happens to be Wi-Fi radio from Espressif, it's also a RISC-V based MCU, but that manages the whole stack, manages the connectivity to the cloud, the authentication in the cloud. It was literally like within the day of connecting that radio up to the MCU emulation platform via a simple UART interface. We had data streaming into our database in Amazon Cloud, and a little Grafana dashboard up showing the data. It was very easy for a development engineer who had never done this before, right? So other than knowing to get the right stream out, a UART port, that's all they needed to know how to do, and then turn on the appropriate authentication in the cloud to let that device actually stream data into our database. So, we probably have firsthand use to be able to tell the attendees how easy it was to actually do. So, mission accomplished on that front.
Good to hear.
Yeah. So yeah, we can still we have till the top of the hour for questions. So if there are here's a question for again for you, Richard. Now that FreeRTOS is managed as an open source project governed by Amazon, how does that actually work in terms of traditional open source projects?
Yeah, well, not much has changed, I would say, from the pre-Amazon days. Amazon obviously have let's step back a little bit. There are millions of devices running FreeRTOS which connect to the Amazon cloud. So Amazon obviously want to make sure that those AWS customers can get connected as quickly and as easily, and most importantly, as securely as possible. So they are investing their own resources in making FreeRTOS, doing things like memory safety proofs, for example, to beef up the security, and investing in cloud connectivity libraries. But also, it's important that FreeRTOS runs very well on the latest hardware, like the CORE-V. You want to make sure it's future-proof, and also providing long-term support, which is very important to their customers. So Amazon are investing in FreeRTOS, but the Git, the license, the Git repos, the process is all still open. And in fact, we try and make sure that everything that's in the FreeRTOS organization in GitHub is completely agnostic of anything. It's all open, using open standards, and so it's very easy for people to see what's completely generic, as FreeRTOS always has been, and what is kind of AWS specific. So there's AWS IoT have a lot of value add services like managed device management with over-the-air updates and code signing and all that kind of thing. But all the protocols used to connect, TLS, for example, TCP, for example, are all open standards. So you can see where that kind of separation is. And as far as contributions go, we are, I would say, investing more in smoothing the wheels there. One of the contributions which we're merging at the moment is actually for the E profile of the RISC-V, which is, I'm assuming is coming from the OpenHW Group. As an open source project, it's better resourced, but still very much open source.
Okay, we've got a couple of questions here around CORE-V availability, but I'll just touch on the e-profile. So all of the RISC-V extension standards work and so on, that all happens inside RISC-V International or the RISC-V Foundation, as does the profile work. And there are several members, of the open hardware ecosystem who are also members of RISC-V International that are contributing to that profile work. But specifically, none of those profile standards come out of the open hardware ecosystem. We get asked this a lot. What's the difference between the Open Hardware Group and the RISC-V Foundation or RISC-V International? So the RISC-V Foundation produces the specs, if you will. Those are the specs for the ISA and the extensions, the profiles, and so on. And this is open hardware ecosystem is an implementation organization. So the CORE-V family is a family of open source cores, as we've talked about, and then all the various implementations into SoCs and boards and kits and all that stuff, all being open source. So I've got some questions around where do I get the core? And so I'll kind of take you through some of that. The easiest thing to do is go to github.com, type in, you can type in core-v, so CORE-V, or you can type in OpenHW Group, Open Hardware Group, and you'll hit the Open Hardware GitHub repos, and you'll see all the stuff there. And that's the RTL, the verification infrastructure, the software projects, some of the collaboration around FreeRTOS is there before it gets upstreamed. As an example, same with GCC work and so on. And that's for the core RTL IP, as well as the MCU, CORE-V MCU, SoC RTL, and the emulation bit streams that you need to go and use that Nexus A7 board. All of that stuff's there. You don't need to be a member, just go get it. If you're interested, I've had some questions around the SoC. How do I get the CORE-V MCU chip? Well, the only way you get that chip is on a dev kit. So the relationship that we have with Global Foundries, as I mentioned in the video, we love Global. They're a great member, and they support us with 22FDX and 12LP wafer projects. So this is a tape out in 22FDX at Global Foundries. And it's not a production device. I mean, the SoC, the MCU SoC is being integrated and verified towards being able to be used as a production device. But as this nonprofit ecosystem, we're not in the business of building and selling chips, and we won't be. So we can produce several thousand, up to 10,000 of these MCUs. We probably never will. And they will be made available only on dev kits. So you can't get the chip by itself. You can get the chip on a dev kit. So if you go to the Open Hardware Group website, so OpenHWgroup.org, one of the top menu items is CORE-V dev kits. And if you click on that menu, you'll see all the information about the dev kit that we presented in the videos. You'll see where you go and sign up to get on the waiting list for when hardware is physically going to be available. And you'll be able to get an order in place for that, or get your name on the waiting list such that you get information as to when you can place your order when that becomes available. So again, a reminder, throw your questions in the Q&A window. Because once we run out of questions, we'll probably just go ahead and shut down the call. So if you have questions for me about the open hardware ecosystem or any of the projects we have underway, or questions for Richard, then let them fly. And Richard, you should feel free to ask me questions too, if there's anything that's on your mind. So there's another one in here, just in general, about the software task group and just software projects overall within an organization called Open Hardware. What is that about? And I'll let you comment on that in a second, Richard. I'll give my views. So we have a pretty active within the open hardware ecosystem. under the technical working group, which is the sort of the engineering or R&D department, if you will, of the ecosystem. There's 4 task groups. There's a cores task group that works on the RTL for the cores themselves. There's a verification task group that verifies those cores. Then there's a hardware task group that implements SoCs and board level product and that kind of stuff. Basically a customer, if you will, an internal customer for the cores themselves. And then there's a software task group. And the number of projects that we have in each of those task groups, actually, the software task group has a greater number of projects than any of the other task groups. And that's usually always the case in most chip organizations anyway. The amount of software that gets written around the SoCs and devices that get developed in a chip company, and the engineers associated with that often far outweighs the hardware developers. So we have a very active software task group chaired by Jeremy Bennett at Embacosm and Yun Hui at Alibaba. And it's a very busy task group. We're working on things like the SDK and the IDE associated with the SDK, both Eclipse-based IDEs, as well as there's a lot of active discussion around Visual Studio work for a CORE-V SDK. We have HAL abstraction layer projects, nascent projects that are being discussed and underway. We clearly have FreeRTOS work, as we've talked about extensively, GCC and LLVM work, Linux porting to the application class cores, different emulation and simulation environment for the software developers to be able to work without physical hardware. So lots of active projects in the software task group. And maybe Richard, you can talk to your team and talk about how your team contributes basically to both of those elements, the software task group and the hardware task group. I know you've got contributing engineers working on different projects within each of those task groups, the CORE-V MCU and the DevKit, and some of the FreeRTOS stuff. What's your experience been like, and how you see that unfolding?
So all the software is an enabler, right? So I think it comes back to what I was saying before about undifferentiating work. I mean, I was using before all the software you need to connect to a cloud, which isn't adding value to your product. And so all the work that's going on with the software task groups is providing that equivalent, if you like, the analogous undifferentiating work. I mean, if you manufacture your own CORE-V device, you then don't want to have to go and start getting a compiler for it, or start porting an OS to it, or doing a device driver or something like that. But these things are just the things that are required in order to add the value, whatever your business logic, whatever value your business logic is generating. You just want to focus on that. So it's an ecosystem of enablement, which is allowing people to just focus on the actual differentiating work as much as possible. And I think that's that in the deeply embedded space, if you're not writing applications, that's kind of what you're doing. I think I always think of FreeRTOS as an enabler to other things. So it's very analogous to the cloud work we do there. And plus everybody brings their own expertise, right? I mean, I wouldn't know how to do the compiler work, for example. That's the collaborative element. Everybody's bringing their skills. And
part of the overall, we still have time for a couple more questions, but we're going to wrap up if we don't have any come through in the Q&A window here in a few minutes. Any more come through. So, part of the makeup of the CORE-V or the open hardware ecosystem overall is exactly that, right? It's great to have a processor core or the IP block of a processor core that you can integrate into an SoC. But the goal of the open hardware ecosystem is to create that complete enablement from application integration at the API application end, right through to the physical design and back-end layout of your SoC at a fab, and everything in between, right? So you would expect to see reference designs of physical hardware with ported software at the OS level, with debug kits and integrated development environment support and compiler support and all of that, and obviously full verification of the RTL itself. But it's clearly not just the core IP and that core IP being well verified. Those are absolutely required, but insufficient in terms of overall ecosystem enablement. And if you look at the roster of close to 100 members and partners in the open hardware ecosystem, it's really a population of all of that enablement, from software and systems and board level and chip level and foundry level companies that are engaged in this ecosystem to make that happen. As always, Richard, it's a pleasure to have you as a speaker on our OpenHW TV episodes, and thank you very much to Amazon for your support. And thank you for attending. We're going to wrap this up, and wherever your day is, I hope is a good one. Thanks. Bye for now.
Cheerio.